Hi, I'm Jeff Ubben, Duke 83. My friend Vijay is with Exxon, 34 years as VP of Research and Development, and most recently the Senior Director of Climate Strategy and Technology. Let me give you some context why we're a team up here. I have been a public market investor for 40 years. In 2000, I started a company to prove out this concept of a shareholder director, where as a large owner of stock in a company, I would go on the board, and I would have kind of all the information as a board member, and then I would work over the long term with the team and the rest of the board on creating idiosyncratic shareholder value. And it worked pretty well. By the time we hit, call it 2015-16, in which we had an election that proved to me that something was different. Maybe there were more people left behind than I imagined. I started to worry about the lack of voice of these other constituents. You know, I was a great profit maximizer. Companies are great profit maximizers, but there's these other voices. There's the customer, there's the worker, and there's natural capital. During the ESG bubble, I decided to apply my energies to these other voices. But I did it differently. I didn't go buy already green businesses. My goal was to work with incumbents that are addressing basic needs like energy, food, and materials, and to work with these companies that have the big balance sheets, the technology, the customer, and the operational scale to do less harm, to decarbonize, to reduce toxicity, to reduce waste. So I was lucky enough to be asked to go on the Exxon board in 2020 for the 2021 annual meeting. And during my onboarding, I was introduced to Vijay, and I feel like I struck gold because you had this person steeped in science that was teaching me, as I want to be taught. I love learning curves. Teaching me about both the potential and the determination of what our 20,000 scientists and engineers that we're going to take on aggressively. We call the and equation, which is to provide affordable, accessible energy and lower emissions. And so Vijay, from the horse's mouth, I'm telling you, this is the man that's been thinking about this. Can you tell us both about yourself and about the role Exxon plays up till now and today prominently in the and equation?
Yeah, well, first off, Jeff, thank you for the invitation. Thank you all for coming here. And for the students here, I understand today's like the midweek break you guys get, and you're still here. So thank you for taking time out of your schedules to come here. Energy has fascinated me since I started, and I started back in 1987, so it's been a long, long time that I've been in this space. I started in research. I then went through multiple rotations with the company, got to see all dimensions of energy, from manufacturing to sales to marketing to planning to you name it. I had the fortune of leading our R&D organization for about 10 years. Where we did the pioneering research on a lot of the things that are common words today, but really weren't common words in 2013, things like carbon capture and biofuels and hydrogen and lithium and things like that. And so all of that really started in our research, because we'll get to in a minute about just the nature of this industry. It's so technical. And then got to know Jeff through that. And a couple of years ago, I was asked to join our corporate office and start thinking about this nexus of technology and policy, and how do we actually navigate the transition. So yeah, I've been very fortunate to have the various experiences I've had, and certainly fortunate to build the friendship that I have with you now, Jeff. So how do we look at this? Let's just take a step back and think about energy for a minute, because it is so complicated. So let's just look at this room. Everything here is energy. Everything here started with energy. And none of you thought about that. None of you. You got in the elevator this morning, you didn't hope the elevator would go down. You didn't hope your lights would come on this morning. Because if you have it, you kind of take it for granted. And if you don't have it, which around 2 billion people are in that bucket, they don't even know it's possible. So the AND equation has multiple contexts. The AND equation is allowing us to continue to prosper, but bringing those that don't have it up to that level. Because you're not going to get there without energy. We'll kind of put some scholastic terms into this. Energy is the ability to do work. That's the definition of physics books. That's what the definition of energy will be. So the more work you do, the more energy you need. That's kind of the context of the discussion we just had on AI. If you're going to do more work, you need more energy. It's pretty simple. It's how do you get the energy? And the scale of this industry is, like, our units are very hard to understand. We talk about exajoules. We talk about terawatts. We talk about all these things that just have lots and lots of zeros. But I want to think about scale in a different way. Engineering, in the context of this discussion, energy requires every discipline of engineering, every discipline. Mechanical, civil, chemical, nuclear, pick them all. Every discipline of science, math, physics, chemistry, biology. Every discipline is social science, economics, more and more public policy, right? The nexus that Duke has with its policy group. We're sitting at a business school, and we're talking about technology. They all have to come together. I don't think there's another industry like that. And of course, our company's been at it for 140 years, pioneering a lot of the technology that people take for granted today. And that's what we're working on now. We're working on the technologies that are going to be needed tomorrow while continuing to optimize and get better and better and better at what we're doing today. So it's not or, it's and. And if you think of this as an and equation, and by the way, and doesn't mean equal. And means both. And so you've got 140 years of doing it one way, lots of optimization, lots of scale already. The other value chains are just beginning. And so we just got to be cognizant that those will take time to grow to scale. So we don't look at this as an equal. We look at them as equally important, but not equal in potential and in speed and things like that. And so as we get into this discussion, Jeff, we ought to just keep drilling away at that, the complexity, and with the audience here, try to explain, one, the complexity, but how we break it into pieces to take what's a really complicated problem and break it into pieces so that we can solve the problem.
Let's just give one example of how hard this is. This is the one thing that bothers me, which is I don't think we were told by Al Gore and others how hard this is going to be. We could just buy renewables, you know, put fossil fuels out of business, everything's going to be cool. And that was, I think that did us a disservice because the consumer hasn't been told that they have to sacrifice something. The companies downstream have to pay more if they want a lower emission product because that carbon-hydrogen bond packs a wallop in terms of energy density, and it's hard to beat it. So you probably are gonna pay more. But Exxon is in the process of building a plant in Baytown, Texas that the plant's already built, but we're spending $8 billion plus perhaps on a blue hydrogen project that will basically be at more than 10% of the total blue hydrogen in this country by 2030. This is a really scaled project. Talk about like how the economics come together, what sort of policy you need to make it work, what have we discovered in the process as we work toward, you know, approving this project?
Yeah, no, that's great. And let's just get everybody up to the same field here in terms of why hydrogen and why we're making hydrogen the way we're making hydrogen. So as you all know, right, in a lot of our processes, we need heat. We need something to go react to give us the temperature that we need to make the reactions occur. And that can be multiple ways. That can be natural gas, that can be coal, that can be, in some cases, electricity. But hydrogen, when you burn hydrogen, there's no emissions, right? So hydrogen is just H2. And so you burn hydrogen, you get water. So you look at that and say, well, that's a pretty good process fluid. Now, how do you make it at scale? And Jeff used a very important word when he said molecules. There's two things that are needed for energy, molecules and electrons. That's kind of the two buckets that you're in. And we, as a company, have lots of skills in molecule management. So we know how to take molecules, we know how to find molecules, we know how to convert molecules, we know how to separate molecules, we know how to use molecules. That's essentially the energy value chain. Find it, convert it, use it. And so we're looking at taking methane, which is 4 hydrogens and 1 carbon, which is the best hydrogen to carbon ratio that any molecule has, and take that methane and convert it to hydrogen. The carbon then becomes CO2. And if you can capture that CO2 and sequester it, you basically have what we call a low emission. Some call blue, we call it a low emission hydrogen, which can be used. So it starts with, do you have a pathway to scale? In this case, we do, because we know more about carbon capture than just about anybody. We know a lot about methane, we know a lot about methane transformation, and so those blocks come together. Now you brought up something else, which is, I think, a really important thing that we need to talk about, which is the technology policy nexus. And here's how I want folks to think about this. Policy can't be there forever. So when you're thinking about policy, you want to have line of sight to markets, because eventually the policy has to move to a market. And with technology, you have to have line of sight to scale. And if you just kind of use that rubric for energy, do I know how to get to scale? Do I know how to get to a market? Then you're on the right path. And that's what we think we have with this hydrogen. That's why we're progressing this project. And we'll see where it goes. But I think those are the types of things that are going to have to happen. And I think we're demonstrating. We're not just demonstrating with hydrogen, Jeff, as you know. We're demonstrating with carbon capture. We're demonstrating with not just carbon capture, but also infrastructure with the pipeline infrastructure we have. We're demonstrating with lithium. We're demonstrating it across the board in a suite of technologies that fall under our low carbon solutions business, which was the other thing we did. Under the AND equation, we recognized, or Darren recognized, that we needed to set up the organization such that we had parts of the organization in the traditional value chains, and then a new organization developing the new value chains. And that's the carbon capture, the hydrogen, the lithium, and things like that, and watching that grow. So he's committed capital to the low carbon business. We obviously have capital to our base business, and now we're going to see where it goes. And again, it's energy is a pretty simple business at the highest level. It's meet demand. And so as the markets evolve, we'll evolve with the markets.
When you think about the current policy, so 45V picks up the hydrogen, and it is in the right direction, because it's technology agnostic. It doesn't pick colors or products even. It tries to measure the carbon intensity, the relative carbon intensity on a continuum, and give you rebates according to the carbon intensity of the hydrogen.
Right.
First off, is that correct? And secondly, is a current policy construct enough to engage the markets? As you said, this idea of policy has to have line of sight of markets. Do we have that or not? So
let's go back to breaking that. I like to take problems and break them into sub-problems. That's kind of what engineers do. So you start with what's a core element of a policy that we think makes sense, and that is that it's technology agnostic. If you can have a policy that lets the best technology win, you probably have the highest probability of getting something deployed. And so that meets that requirement, because it says you hit a certain threshold, you get that. Now you need to make sure that all the value chains and all the different ways are recognized, and you have to allow for innovation. So you want to continue to allow people to improve and get credit for their improvement. So That simple value chain to make hydrogen includes things like not releasing methane when you're getting the natural gas. So we have very aggressive targets to lower methane. We have 2030 targets for our Permian assets. We've reduced our methane intensity by 60%, et cetera. But you want to be recognized for that. You want to be recognized for what we call system integration when you're building your process integration. So all those things have to be recognized, and I think we're making progress on.
System integration is the pipe that we own that runs from the Permian to the refinery, let's say. It's not a leaky pipe.
It's not a leaky pipe, for instance. It's also how you run your Baytown operation, how you do heat management, how you do byproduct management, all those types of things, right? It's simply put good business to make the most out of every molecule that you're touching, right? That kind of makes sense. And so you want that to be recognized. And so I think we're moving in the right direction. I think the discussion has to continue, Jeff. I think we're seeing signs of good policy. We're also seeing signs of things that we'd like corrected in other things. But that comes back to this and equation, where you have to have the right constructive discussion going. Because I really do think everybody has the same problem statement, right? The problem statement is more energy, lower emissions. We got to if you agree on the problem, you have a much higher probability of getting to the answer. If you don't agree on the problem, then it's a lot harder to get to the answer. And that's why we spend so much time on the problem statement. I know there's a lot of students in here, and when you're an engineering student, if we go back to, we were undergrads at about the same time, as you could tell by our biographies. I remember, and I was a Purdue undergrad, you're an engineer, and the first thing they tell you to do is read the problem. Second, they tell you is reread the problem. Then they tell you to write down the problem. Then they tell you to draw a picture of the problem. Then they tell you to write down the assumptions embedded within the problem. You are 5 or 6 steps before you even start trying to solve it. Just making sure you really understand the question. And actually, that was part of our credit. I got through college on partial credit. I don't know about you guys, but there was a lot of partial credit if you went through that discipline of understanding the problem. And that's why I keep coming back, Jeff. That's why I keep coming back to, we just got to make sure we have the problem statement. Mm-hmm. And we got to make sure we're aligned on the problem statement. The problem statement is more energy, lower emissions. And I think if we can move down that road, then I think we'll find a lot more agreement than disagreement. Because I can't believe anybody would disagree with that problem statement. We need more energy, lower emissions.
Okay, so I called Vijay in a panic about a year ago as I realized they made AI about national security, so it has an imperative once you define AI as a national security issue. And so the ability of the hyperscalers to use fossil fuels to drive data centers was obvious to me that it was going to happen, because you got to energize these GPUs. The GPUs are so expensive. You have to energize them, and you'll pay a lot to energize them, which holds great potential to do low carbon or low emission solutions. But the scale isn't there, and so here we are switching coal on for data centers. And so I said, Vijay, how do we make these guys pay for the externalities of their product, or are they just going to have a license to emit? Because other people don't have that license, by the way, but these AI guys do. So how do we do this to make this, quote, new technology, which has to happen? We have, this obeisance to progress. This has to happen. How do we make the externalities somehow be accounted for finally in this, new technology that's going to just run like crazy? And so Vijay has worked on a concept of carbon accounting that I think is very relevant. Can you talk about that?
Yeah, so let's start with AI and just put that in context, because it actually goes back to my opening statement, which is more work requires more energy.
Right.
AI is just the ability. AI does a lot of work, and I'm going to ask the students here, I'm going to use an analogy here. You are going to have to YouTube it tonight to know what I mean. But we're the slide rule generation, okay? Half of you don't even know what a slide rule is, so you can look it up.
My dad used a slide rule, I remember that.
Yeah, I thought a slide rule was magic, because I was like, how in the world can this little thing tell me how to multiply all these numbers and do log scale and all that other stuff? And then we went from that to a calculator, to a computer, to supercomputer, and now we have AI. And each time you add computational capabilities, you unlock all sorts of potential. So I'm super excited about AI. I'm super excited about quantum. I think this whole computational capabilities is actually going to be critical enablers in optimizing the grid and designing materials and optimizing processes. But they're going to require energy. And we want to make sure we understand the implications of the energy choices you make. And that comes back to the carbon accounting. So what is carbon accounting? And we're sitting in a school of business, and so I'm not going to try to give you all an accounting lesson, because that accounting kind of puzzled me as an undergrad. But you've got to be able to understand so we're talking about emissions accounting now, CO2 accounting. So how do you track the CO2? And we know from adjacent industries that if you know what your sulfur is in fuel, or your miles per gallon, or any type of a calculation of what the intensity is of your activity, it drives behavior. And so Jeff and I have been talking about that, which is, okay, well, you should know what the CO2 per watt is for your power, or you should know what your CO2 per byte is for your computational, or your CO2 per search, or something. How do you do that? Because I can't actually take out my phone and get a number. So you have to have an underlying calculation methodology to do this, and this is what we've been talking about, which is we don't really have that today. There isn't really a systematic way to be able to compare one pathway versus another, and that's the work that we're trying to progress, which is we need an accounting framework that can allow you to understand where the emissions are, where they're embedded in a product, and how those CO2 emissions flow through the economy. Now, what I just described for the business school students is a ledger, okay? That was a very complicated way to say ledger, but engineers don't really use ledgers, right? Accountants do, but this is the and equation again, where engineers and accountants need to get together, and it's chemistry plus accounting in this case, that allows you to then track CO2s as a liability, meaning it was an emission, or as an asset, meaning I pulled it out. I pulled it out of the air. Okay, well, now you know it's only two components, right? That's the beauty of accounting. It's either a liability or an asset. And if you can start to track the value chain through that, and look, we have certain tools that do elements of this. I mean, the GREET model that the DOE runs is an element of this. It's not that there's nothing out there, but there is nothing out there that does what Jeff and I are describing here. And that's what we're proposing. We're saying, look, we gotta take a look at this and say, how do we actually get the right calculations here, because it can't be measured. What are the right calculations here that can allow transparency so that decisions can be made, right? Again, the art of accounting is informed decision-making, in essence. And so how can we apply these kind of engineering tools, the laws of system boundaries and material balances and energy balances, to an accounting, a ledger, and see how that flows through.
So this is Vijay's idea. He's been championing it for a few years now, and for me, it was like an epiphany, because if you think about, 1929 and the crash, we didn't have financial accounting, and therefore we didn't know if we could trust the balance sheet of the company that we were invested in, so we just sold it. And it wasn't until 1933 in the Securities Act where we codified financial accounting, and then subsequent mechanisms like the FASB were formed, and now we trust accounting to the point where it's 99.9% accurate, and it runs the world, this hyper-financialized world of ours. We when you think about carbon accounting, so we have the financial crash, now we have a climate crash. So of course we need accounting to make it work. And so, this is to me is, if you think about GHG protocol, it doesn't really, that's not the math. Right. We need to do the math. GHG protocol makes Exxon responsible for the whole supply chain of CO2 emissions. It's performative, it overstates Exxon's, problem. Because I think at the core, GHG protocol probably wants the oil and gas industry to self-liquidate. I mean, that's just between us here. But it's not the math, it doesn't follow the math. If you take an airplane trip, Exxon originates the molecule, there's a CO2 that's released. It hands it off to the refinery that distills it, CO2 is released, but it's only released once at each process along the way. There's a logistics company that moves it. Maybe they have an electric truck that moves it, maybe they don't. And there's an airplane company, there's an airline, Delta Airlines has bought a fuel-efficient plane, or they haven't. And that you sum up the whole supply chain CO2, and you say your CO2 per mile is X. Okay, now we're in business, because if you set a standard according to the CO2 per mile, as the government has done and other things, the supply chain will start to solve, the markets will switch on, the supply chain will start to solve for the most low-cost way to hit the standard. And Exxon will be rewarded for their low-carbon molecule in the Permian, and the refinery that's using, less carbon-intensive hydrogen will be rewarded, and so forth and so on. This is how we switch the markets on, right, which, in my opinion, have not been switched on. The IRA is a subsidy that can be taken away. It will break the bank if we try to subsidize our way through this. The markets are not really switched on. Would you agree with that?
Well, I think the data is the data. Energy demand is going up, emissions are going up. These are just facts. I agree that the more we can have transparency in where the CO2 is emitted, I think that's better. I don't necessarily make it personal. I think what we need is a transparent system to be able to track CO2. We have systems out there today. They're complicated. They do things that don't material balance, to use an engineering term. So there's double counting, there's triple counting. It's hard to really know which step is being taken by whom to make sure we're curbing emissions. And so what we've been talking about is, how do you develop an accounting system that allows you to do that? And we get into that, and if you go to our website and you see this thing called Advancing Climate Solutions, which is our annual report that comes out, we go into a little more depth around talking about this. But I think Jeff hit the fundamental points, which is the simplest concept here is you track the CO2, and CO2 only occurs once. That's the chemistry piece of this. You know when it occurred. That's your T equals 0, so you know when it appears on a ledger, and you just track it through a ledger. And that will give you that type of transparency. We're confident that if you had that type of transparency, you could then set these standards, and you could then tighten the standards over time. And it's been proven in other areas, and so we're trying to do what makes engineering and kind of this whole space exciting, is we're trying to learn from what's worked in the past. Quite frankly, we're also trying to learn from what hasn't worked in the past. The art of an experimental design is to both have positives and negatives, and try to minimize your negatives and maximize your positives. And so there's good in a lot of things out there. We're trying to connect all the goods, but we're also being sort of humble and saying, but there's some gaps, and we think we need to close the gaps. And so learn from financial accounting, which is another, as you know, financial accounting is nothing more than calculation-based methodologies. There is no real measurement going on. And so how do we do the same thing here in CO2? Because as you know, CO2 is essentially not measurable, but it is calculatable. Other things are measurable. Sulfur is measurable, other things are measurable, CO2 is not, and that's why you need this calculation-informed methodology that can have measurements around it. You know your flow rates, you know your your feed rates, all these other things. But at the end of the day, it's following the calculations through the value chain that we think is going to work.
How achievable is this? So, when you talk to the GHG protocol, the science-based targeting guys, they argue that this is not that doable. They want to stay at the company and country level, not the product level, because they find it to be daunting. And so, what's your response to that?
Well, again, I go back to we gotta just continue to work together and explain what we're doing. I think we have to publish what we're doing. I think we have to get out there and explain what we're doing, because anytime you come up with a new concept, you expect an incubation time, if you will. And so that's the beauty of doing these types of sessions, where we can come out here and start talking about these types of things. That's what we try to do in our ACS reports and the various things we put on our websites as well.
But what would you do? Would you form an FASB for climate, for carbon, or what would you do?
Yeah, I mean, this is where I kind of rely on your judgment as well, because I think you know this space probably better than I do. From my space, I'm trying to make sure that we have the math right, that we have the chemistry right, that we understand how the math and the chemistry work together. And then we're going to have to bring in the right types of people that understand how to take something like this and build a construct. And so while you've been very complimentary to me, I'll throw the compliment back to you, because you've taught me a lot about how these systems work and how these other processes work. So, but it really does start with, you got to do the math.
Right.
Okay, you hear our chairman say that all the time. We've got to do the math. And if we let the math and the chemistry guide us, I'm a big believer that if we let science guide us, we're going to keep going in the right direction. There should be fewer arguments if you're math and science-based, because it's the math and the science. It's just the math. And so the more we can boil this down to it's just the math, I think the higher the probability that we have alignment as we go further. And then the final thing that we really haven't talked about in this discussion, but this very thing is going to be maybe the most important thing that we do over the next few years, and that is talk about this. Is to have that inclusive discussion where, all right, we don't have to agree on everything, but let's find the areas where we do agree. And let's keep connecting the yeses. It's very difficult to connect no's. It's actually very easy to connect yeses. And so let's start at the basic thing, which is I started with, do we all have the same problem statement? Because if you don't have all the problem statement, you're kind of done there. Do not pass go, don't collect your $200. Come back and say, do we have the right problem statement? If we have the right problem statement, okay, let's go to the next statement. And if we can keep going down that pathway and having this type of discussion, and I think in the last few minutes here, we ought to turn it to students, because we are here at Duke. And look, we need the best of the best. This is arguably one of the toughest problems we've ever had internationally as a society. How do we continue to grow energy and lower emissions? How do we continue to improve quality of life and respect the planet? How do we do both? And we got to get students to understand that. And we have to have students studying it. And I know Duke's got some fantastic programs between the engineering school, the business school, the policy school. And I hope the students in the audience and I hope the faculty in the audience is taking that away from this, Jeff, which is we really have to work together. Collaboration is the other key word here. So and is a yes type thing, or is a no. So we like the yeses, so let's go with the ands. Let's think about different types of collaboration. So we need collaboration between companies and universities. The US obviously has national labs. We need national labs collaborating. We need small companies. There's some small companies here. We need large companies. Panel before us had the investment community. The investment community has to work with our. It is all about these different types of collaborations, always coming back to the problem statement. And anytime we're hitting a disagreement, we need to come back to the problem statement and saying, okay, are we moving down the field towards the problem statement? And so if you took one thing away from this, it is the problem statement. And it is the problem statement, which is more energy, lower emissions, quality of life, technology, policy, working together. Energy has evolved, just in our careers. I'd never, if you'd give me a blank sheet of paper in 1987 and said, describe energy in 2025, I'm pretty sure I'd have failed that exam. okay? And that in itself is all because of technology evolution. The things we're able to do today were unimaginable. The computational capabilities today, unimaginable. So I'm not gonna imagine, people want to imagine 2050. The only thing I know in 2050 is the technology is gonna get better, societies are going to improve, and if we work together, we'll accelerate this space. And so that's really the key takeaway from this discussion.
How much time do we have? Are we done? Should we take 1 minute? Okay. Are we taking questions or not? I don't even know. I have one point that I want to make, because if you let Vijay run on this, this idea of an asset and a liability, and so Duke is net zero, but we did it with a lot of carbon offsets, and we did our work on the projects that we're using to offset our carbon emissions. But if you get to the point where you have accounting that allows you to set up an asset because you planted a tree and then as soon as that tree burns or gets cut down, it turns into a liability because you emitted the carbon. You start to bring the math to nature-based solutions that gives it integrity. And then you start to let the market solve for it. So for instance, that's a pretty low quality asset because it can burn tomorrow. So you wouldn't put a lot of value on that asset. But if you do direct air capture and you're putting it into the ground for 50 to 100 years, that asset then has a lot of value because it's sequestered and it's warranted by Exxon that it's not, quote, leaking. And so then you can see that asset is highly valued, and you can watch the market start to solve for the permanence of the carbon sequestered. And this is, back to where we started. The markets aren't switched on. We need the information in the math to do so. And the work that Vijay is doing at the
Although
forefront.
I think the student just became the teacher. Okay? I think that's what we just witnessed.
Yeah. Well, I'm just regurgitating what you tell me. All right, thanks for your time.
Thank you. Thanks, Jeff.